Oh, really?
No, it's wear like a thing.
Oh, you're so right. I thought that was their hair. That's my bad. You're right, they don't have hair.
All righty. Recap, as always. Are you guys studying for the quiz on Friday?
We'll start. Oh, working on start now.
All right, let's do some recap. What is supercritical fluid chromatography? How would you define it? What's the stationary phase? What's the mobile phase? Why is it called supercritical? Any thoughts? Guesses? Huh? What's supercritical about it? It's supercritical because what's the mobile phase? One word, anybody. Huh?
Polar.
Well,
It's not one word.
there is, yeah, okay.
It's the supercritical pressure and temperature. It's the high, too high of pressure and temperature.
Yeah, so if anybody remember that it is CO2 under supercritical temperature and pressure becomes liquid, fluid,
It's like,
huh? It's coming back to you. Yeah. So the mobile phase is CO2 fluid under supercritical pressure and temperature. So it's compressed gas and then it has fluid properties now. And it is less viscous, helps with better movement. And it's usually supercritical chromatography used with components that are not thermally stable. They cannot be volatilized, so we can't use GC, or we can if we derivatize, but it's not very good for GC application. And then we can use supercritical using HPLC types of stationary phase and detectors that are GC, typical of GC detection. All right. All right, there's only one slide on that, so just try to remember these key points for supercritical. What is reversed phase chromatography? What is the stationary phase? And what's the mobile phase? Polar, nonpolar, stationary nonpolar, and mobile phase is polar. And the only reason it's called reverse phase because it was discovered or used after using normal phase, which is the stationary phase is polar and mobile phase is nonpolar. So the only reason one is called normal and the other the reverse because one came before the other. So it is reversed to the normal phase. Okay, so in reversed phase, paper chromatography, what type of compounds travel the most with the mobile phase? So reversed phase paper chromatography, meaning we're impregnating the paper with a nonpolar solvent. Instead of impregnating with water, we're impregnating with nonpolar solvents, so your stationary phase is nonpolar, and the mobile phase is the water, which is immiscible with the organic phase. So what will travel the most, polar or nonpolar compounds? They move the most with the water. Polar. So they don't want to stay sticking to that nonpolar phase. They want to move with the polar phase. So the most polar will travel the fastest. What does TLC stand for? What did you say?
Thin layer.
-2. Oh, he wants standard love and care now. What was the other one? Teaching something? The learning. Yeah, okay. So it's thin layer chromatography.
yes.
How does it differ from paper chromatography? What are the advantages of thin layer chromatography? Do you have any remembrance of that? Yes, Lukman.
So better
Better?
resolution.
Better resolution because the particles are fine particles, well distributed, very thin layer. We have better consistency, better reproducibility than the cellulose paper that could have different thickness. Not the particles are not as finely distributed as in silica, for example, silica gel made up of finely powdered or finely ground particles. All right, what's the difference between isocratic and gradient elution? What do we mean when we say isocratic elutions? Yes, go ahead, Emma.
Stays the same.
The mobile phase
While
stays the same.
it's not changing.
Mhm.
The gradient is where it changes through time.
Exactly. So isocratic elution, meaning we use a mobile phase at a one concentration and it doesn't change throughout the analysis time. Stays the same concentration, same flow rate, same everything, the entire analytical run. Whereas gradient elution is what? Those of you that did the HPLC today. Did you use gradient elution today? Yeah. So what did you do with that? Changing the concentration over time. So in gradient elution, the mobile phase composition, concentration, whatever it's made up of, will change over time to enhance the analysis time, reduce the analysis time, prevent a compound from staying too long on the cone, on the stationary phase. Okay. And when we say increase the strength of the mobile phase, what do we really mean? What do we really want to accomplish? Increase the strength of the mobile phase.
Isn't it just changing the concentration?
Yeah, to what purpose? When we want to make it stronger in what term? More polar, less polar, what do we want to do? Help the compound come out. So meaning help the compound like the mobile phase better. So now the mobile phase is stronger for that analyte. And it could be in any direction, depending on your mode of separation. If it is a normal phase, then we increase the water concentration because in normal phase, your mobile phase is nonpolar. However, if it's reversed phase, like the case of caffeine that you analyze, you start with mostly water, 99% water, so you increase the organic solvent over time. So both cases, you're increasing the strength, the power of the mobile phase to get those analytes sooner out of your stationary phase, to make them like the mobile phase better. Again, the justice example, give the kid buy them something so that they come up. So make the mobile phase more likable to the analyte. That's what it is. Okay. So, like I said last time, when you're studying, just make sure you go back to these recap questions and be able to answer them. Look at the quiz questions from last year. Look at the student learning outcome documents with what you need to know about chromatography and other sections that you are studying. All right. So I moved a couple of things, a couple of slides in different orders because it made sense more to talk about partition first, because in paper and thin layer chromatography, they are partition chromatography. So I wanted to continue talk about column liquid chromatography by talking about partition first and then adsorption. So you have those slides, I just moved the order. Okay. So we already know partition chromatography, your mobile phase is liquid, your stationary phase is liquid. So whatever you are trying to separate, you are separating them based on their partition coefficient. how much they like phase 1 compared to liking phase 2. That means how much they like to interact with the mobile phase and how much they want to stay dissolved in the stationary liquid phase. So the elution of the solutes depends on changing the nature of the phases. So we can, that means we can increase the strength of the mobile phase either by changing the constitution of the solvents, percentages of solvent, or changing the pH. And we also can later on talk about other ways of changing the strength of the mobile phase. And we already said that for normal phase, when the more polar phase is, when the more polar phase is held stationary with a support, then this would be normal phase. And usually in normal phase, your stationary and mobile phase are immiscible. Water and hexane, they're immiscible. I mean, cannot mix into a homogeneous solution. That's what normal phase chromatography, the two phases are immiscible. We are going to talk about hydrophilic interaction liquid chromatography, which also you can separate based on the polarity of the components. And it is under normal phase. The only difference is that the mobile phase is actually not an immiscible solvent. It can be mixed with water. And I'll tell you why this is advantageous in later. So both stationary phase is polar, the normal phase and the hydrophilic interaction chromatography. In both cases, your stationary phase is polar and the stationary phase is liquid in both cases, but there are slight differences that I'll talk about in a later slide. Now, when we flip it, reverse it, non-polar is the stationary phase, then it becomes reversed phase. So, all right, so now that concept is becoming a little bit more familiar as I repeat it. Okay. So you have a support, usually it's silica, and then it is impregnated with water or hydrated, then it's called silica gel. Then the water is your stationary phase, and that would be normal phase. Sometimes we have bonded support. So there's the coated support, just, water is loosely bound, coated, or you do have chemically bounded, like covalently bounded support. But these are more common. I'll talk about it more for adsorption chromatography, where actually you have a hydrocarbon attached to make it a nonpolar. So silica is covalently linked to C8, C18, like in the caffeine lab, or C40. I'll talk about it under adsorption chromatography. These are chemically bound to silica to make it more nonpolar. So hydrophilic interaction chromatography, how is it different than normal phase? So it is polar. So you have all interactions, van der Waal, electrostatic, hydrogen bonding, all polar kind of type of interactions. So, and then you have a silica usually as your stationary phase bonded to amine, cyano, or cyclodextrin, polar components. Now, the mobile phase in this case is not hexane, not immiscible with water. It is actually miscible with water. Like acetonitrile, you can actually mix it with water, and usually it's 50 to 95% acetonitrile in contrast to water. So that's the difference between a normal phase and the hydrophilic interaction, is in its mobile phase. The mobile phase, instead of it being immiscible with water, is actually immiscible organic solvent. That's the difference. Now, why did we go with hydrophilic interaction chromatography? Why not just regular normal phase? There are reasons. Sometimes you have components that don't interact really well with reverse phase. So you really want it to have more interaction with the polar stationary phase. But then these components are not very well soluble in water. So you really want to try to make them more soluble in your mobile phase and the stationary phase. So you make that stationary phase, if it's water, then you make the mobile phase something that has water and has acetonitrile in it. So instead of using reversed phase, you use hydrophilic interaction chromatography. You get these compounds to interact with the hydrophilic stationary phase, but at the same time, they can be soluble in the mobile phase. If you want to have mass spectrometry as a detector, hexane doesn't work. So you really need a mobile solvent that can be used in GC, and acetonitrile can be used in GC. So if we want to use hydrophilic interaction, we cannot use normal phase and link it to mass spectrometry. So we can use hydrophilic interaction chromatography and link it to mass spectrometry, because acetonitrile water is a better mobile phase to interface with mass spectrometry. So these are the reasons: the solubility of your components and the interface with mass spectrometry. That's why there is hydrophilic interaction chromatography. And commonly it's used to determine amino acids, peptides, organic acids, monoacylglycerides, or short chain fatty acids. Okay. What is correct here? Huh? C is correct. Only C? C, D, and B. Yeah, B, C, D. So it is hydrophilic type of interaction. So electrostatic hydrogen bonds and van der Waals are non-covalent hydrophilic type of interactions. Okay. So adsorption chromatography, this is basically your stationary phase is solid, and it's called adsorption because your components are going to adsorb, not dissolve in. In partition chromatography, you have dissolving in the stationary phase and partitioning and dissolving in the mobile phase. But here, adsorption is interaction by adsorption on your solid stationary phase. So the stationary phase is a fine powder that is solid in nature and has specific functional groups. So these red triangles are representative of functional groups on the solid phase that will interact via non-covalent interactions, all different types of non-covalent interactions with those functional groups on the solid phase. Now, what I'm trying to demonstrate here that you do not have a constant partitioning coefficient. So in partition chromatography, partition coefficient is constant. So at equilibrium, you get a constant value, which is the concentration of solutes in phase 1 over the concentration of solute in phase 2. But here, adsorption coefficient is not a constant because it is concentration dependent. What does that mean? That means if you inject a sample that is too concentrated, we will saturate all possible sites, and then some will not find anywhere to interact, and then will elute, leave the column without any interaction. And that is give you a flawed result. You did not allow your components to interact by just using a high concentration. So at equilibrium, you don't have a constant adsorption coefficient because you used really high concentration. That's why oftentimes you have to not overload the column. That is a very common chromatographic technique. Do not overload the column because you don't want to saturate all possible interaction or functional groups that interact with your solutes. So adsorption coefficient is not a constant, unlike partition coefficient, because of this limited number of functional groups that could interact with your solutes. All right. So adsorption chromatography can also be used to separate compounds based on their polarity. So for example, if we have silica, then we have polar interactions. So you can use them in normal phase or in helic. You can use them as reverse phase if you bind a nonpolar component. So 8 carbons, 18 carbon chain, or 40 carbon chain. The longer the chain, the more hydrophobic you're making your stationary phase. So it depends on what we want to separate. For example, in the caffeine lab, we use C18 column. So alkaloids like caffeine interact very nicely with the C18 column for stationary phase. However, if we want to separate carotenoids, they want stronger hydrophobic interactions. So we use C40 usually for carotenoids. So the longer the hydrocarbon, we can make it more hydrophobic. And these are chemically bonded to silica. So in this case, whether it's normal phase or reverse phase, they're going to separate based on the relative polarity as well. And because the mobile phase can compete with the solutes in interacting with the stationary phase, that's why if you increase the strength of the mobile phase, the solute will like the mobile phase better. The mobile phase will start interacting more with the stationary phase. Then we have faster elution. And that is exactly when we say changing the strength, we are altering the affinity of the solute to the stationary phase. Okay, you can interrupt me for questions. All right, hydrophobic interaction chromatography is a form of adsorption chromatography, but it's very specific. The interactions in this case are weak hydrophobic interactions. And the stationary phase is solid, the mobile phase is liquid, hence it is adsorption chromatography. So it is a form of adsorption chromatography. So did you break your computer? Oh, iPads. Okay. So hydrophobic interaction chromatography is a form of adsorption chromatography, and that's why I moved slides a little bit. So like we said, reverse phase with the C18 is an adsorption chromatography. Here, it's also an adsorption chromatography, but instead of reversed phase, it's a specific hydrophobic interaction. So in this chromatography, it is specifically used for biomolecules with protein components. So they would interact with your stationary phase via weak hydrophobic interactions. So very common stationary phase is this a hydrophilic support, but is bonded to a hydrophobic ligand. Butyl cephalose is a very common stationary phase used, where mostly proteins is what you are separating in this type of chromatography. They interact via weak hydrophobic interaction. When it's very strong hydrophobic interaction, we have something we call fouling of the column, meaning the protein gets stuck on the column and they won't come out, and you lose the ability to separate. So that's why we try to have ligands that bind weakly. That means weak hydrophobic interaction, as weak as we can get. So the mobile phase is a salt solution. Most commonly, it's 1 molar salt solution. A specific salt is commonly used is ammonium sulfate. And the way to increase the strength of the mobile phase in this case is reduce the concentration of the salt. I'll tell you why, and what does that mean? You know, proteins have charges on them. You all know this. They carry charge because of the amino acid charged components, the amine group and the carboxyl groups. So when you put salt, you put that protein in salt solution, you are shielding those charges on the protein. So the salt interacts with the protein, so now you don't have charge. So the protein hydrophobic surface will interact with your column. So when you, in the presence of salt, I repeat, the protein becomes mostly hydrophobic on the surface because the salt covers the charge. The protein becomes mostly hydrophobic on the surface and will interact via hydrophobic interactions. So under high, you see that red is more intense, and that red is for hydrophobic surface. Hydrophobic interactions happen, and the most hydrophobic protein will interact the most. So if you're trying to have, if you have proteins in a mixture and you're trying to separate hydrophobic proteins from less hydrophobic proteins, then you can separate them by hydrophobic interaction chromatography, HIC. So now the protein is interacting with the column. How to get the protein out? Reduce the salt concentration, make the solvent more water-like. Once you reduce the salt concentration, the protein starts gaining charge and will start go into the water and then leave the stationary phase. So in this case, we start with very high salt concentration and go all the way down to water and separate the protein based on how much hydrophobic these proteins are on the surface. All right, so you go from 1 molar concentration of salt. Sometimes if you want to separate the protein, you go from 1 molar to 0.7 to 0.5 to 0.2 to 0 water. If you don't want to separate the protein and you just, let's say you want to separate protein from carbohydrate, you go from 1 molar salt to water. Then you get all the protein out together. If you're separating them from something that is not hydrophobic on the surface, like carbohydrate. So it depends on the purpose of your experiment. All right, so in hydrophobic interaction chromatography, interaction between the solute and stationary phase are mostly in hydrophobic interaction chromatography, interactions are mostly hydrophobic. It's not a trick question. All right. Ion exchange chromatography, which is the most complex among all of the forms we talked about. So it's another form of adsorption chromatography, but it's a specific adsorption chromatography. It's based on ion interaction or ionic interaction. In other words, electrostatic interaction. Charges. That's why it's called ion exchange, because it's a very specific type of interaction between the solute and your stationary phase. It's based on the charge and opposite charge, because same charge will repel each other. So if I want to separate positively charged molecules, I need a stationary phase that carries a negative charge. Otherwise, I won't get interaction. In this case, it would be positively, it would be cation exchange. If I want to separate negatively charged molecules, I need a positive charge on my stationary phase, and then it will be called anion exchange. Right? Let me draw it again. I said I mentioned it before, but I want to make sure this is, because I know this is the most confusing bit. When you hear the word anion exchange and cation. So anion exchange and then cation exchange. So the exchange is between what and what? When I say exchange, what is being exchanged between what and what?
Opposite of a negative term.
Yeah, but I'm exchanging between mobile phase, so you have the stationary phase, and then you have the mobile phase. So when you're studying, you have to really visualize this so that you would remember the different charges involved. All right, so my mobile phase, and then when you are separating, you have a mixture of compounds, and then they go between the stationary phase and the mobile phase. So they are being exchanged, like money going back and forth, exchanged. So you are exchanging your ions between the stationary phase and the mobile phase in this downward direction, leaving until they leave the column. So they're exchanging. So in the case of anion, your molecules are what? Negative or positive? Negative. Okay, so, and they carry different density of charges. This has 4 net negative charge, 3 negative charge, 2 net negative charge. There are different density of charges. And the one that is most negative will interact the most. And the least charged will elute first. So that would be the order of elution. So if I want my negative ions to interact with the stationary phase, what should be the charge of my stationary phase? Yeah, negative interacts with positive. Like charges will not interact. Rule number 1 in chromatography. What is rule number 1 in chromatography? What's the number 1 thing you want to happen in chromatography? But in order to separate, what do you want them to do? Interact with the comp. You have to remember this. That's kind of, once you remember this, everything else will be easy. If your components do not interact with the column, there's no separation. They're gonna all leave the column together. For separation to happen, we need to have interaction with the stationary phase. And in order for these anions to interact with your stationary phase, what should be the charge? All of you should answer this now. Tell me, Alan, say something. In order your negative charge to interact with the stationary phase, what should the stationary phase carry? Yeah, so you all know this. You all know this. So this is great. So in anion chromatography then, in anion chromatography, anion exchange, your components are negative, your stationary phase is positive. So anion follows the ions, the molecules, the components you're trying to separate. All right. In cation then now, what's the charge of your stationary phase? Huh?
Negative.
Negative. So in cation exchange, it's the opposite. These will be positively charged. And now these are negative. All right. Are we good with that concept? What's number one that should happen in chromatography? Column interaction. Your molecules should interact with the column. If they don't interact with the column, you're not going to separate anything. Now, going to this, so our interactions is electrostatic because it's ions, so positive and negative charges will be interacting. So the resin here is a polymer. The stationary phase is a polymer, and it carries a functional group with a charge on it. And this polymer or resin would be highly cross-linked. So a lot of cross-linking, highly cross-links. The pores are small. When you have high cross-link, pores are small. So it is for small molecules, like sugars, for example, or amino acids, or organic acid. So small molecules. Whereas if they are lightly crossed, meaning you have large pore size, then it can be used to separate large molecules, like protein is a large molecule, or nucleic acid is a large molecule. So depending if you are separating small molecule, you need high cross-linking, large molecule, lightly cross-linked, meaning larger pore size. So there are two types of resins or polymers used in ion chromatography. Polystyrene polymeric resin, so it's a polymer made with divinyl benzene and styrene. It's not very common. What is more common is the polysaccharide-based resin. So it is made up of polymers of glucose units, and the OH groups in the glucose units are derivatized, meaning the OH groups get chemically linked to either a weak acid or a strong acid, or a weak base or a strong base. All right, so weak acid, strong, intermediate, strong acid, that's strong acid, and weak base or strong base, these. Okay, so a weak acid or a strong acid carry negative charge. Acids give their protons, that's why they're acids. So they give out their protons, so they're negatively charged. Let's see the concept. If you have a polymer that is derivatized with an acid, weak or strong or intermediate, doesn't matter. Is this for anion exchange or cation exchange? Thank you. It's for cation exchange. Yes. So if your polymer is derivatized with an acid, it carries a negative charge. So it's a cation. The opposite is true for base. If your polymer is derivatized with a base, the base usually like to keep the protons to themselves. So they will be positively charged, then it is anion exchange. So let's add a little bit more of complexity. So if you have if you have your polymer derivatized with a strong acid or a strong base, meaning a strong acid will be mostly negatively charged. Strong acid means they give their protons very easily and they resist taking up the protons. So they will be negatively charged no matter what your pH. A wide range of pH above pH 2, they will always be negatively charged. Strong acid, always going to give you your proton. Dissociate very easily, gives the proton. Strong base is the opposite. Will hold on to the proton over a wide range of pH. All pH is below 10, it will be positively charged. Now, weak cation exchanger, meaning weak acid. So it can pick up proton easier than a strong acid. So it works, you can change the strength of the mobile phase by changing the pH. So you can change the capacity of the cation exchanger by changing the pH. Same with weak base or weak anion exchanger gets deprotonated in moderately basic conditions. So if you change the pH, you might lose that proton very easy. Now, why is this important? You might wonder, why is Pam telling us all this confusing stuff? Because when you choose your chromatography, sometimes you have to choose between, do I want a strong anion exchanger or do I want a weak anion exchanger? Meaning, do I want a strong base or do I want a weak base? I'll give you an example where you want a strong base and an example where you want a weak base. So let's say you have an interest in molecules that are positively charged. And in the mixture, you have negative charge molecules. You don't care about those. I don't care. I want these. And you don't want to separate those. You just want them to come out. So in this case, I can choose a strong acid. So that means strong cation. So by choosing a strong cation exchange, I'm going to hold on to these, and then this will elute, will not interact. And that's it. The story is done. But if I have a mixture of positively charged molecules, but all of them have different charges, and I want to separate them. So if I want to do that, I might want to go with weak acid cation exchange, because then I can change the pH of the mobile phase, and then I can change the affinity of the column to my components. So I will just change the pH of the buffer that I'm running. So let's say I can make it more basic, increase the pH. Or I can decrease the pH. Let me go with decrease the pH. What will happen? If I decrease the pH, so my weak acid will start being positive because now I'm adding more protons to my buffer. So my weak acid starts getting protonated, so there are no more interactions because then they lose the negative charge. if I decrease the pH. That means I add more protons to my mobile phase, the protons will displace these molecules. So changing the pH, or I can add salt. If I add salt, the Na plus, will also displace these, and then they will leave the pump. So usually I pick weak acid and weak base exchange if I have very similar molecules with different loads of charges, so I can change the pH and adjust the strength of the mobile phase. All right. What kind of interactions? Electrostatic. Yes, electrostatic interactions. All right, so yes, go ahead, Lizzie.
For can you change it from a strong acid to a weak acid? Which of the cations would elute first?
Yes, good question. If I'm doing weak acid, so this example here. Let's assume I'm doing weak acid, it's negatively charged at, say, pH 4, pH 5, it's negatively charged. And now the ones that are carry more positive charge will have stronger interaction. And so all of those positive charges are going to interact, but I want them to separate. And I want this to come first, this to come second, this to come third. So I start gradually increasing the acidity of the mobile phase. So if I increase the acidity of the mobile phase, it's going to protonate. So I will lose the charge. So this will come out first, gradually. So the more positive they will still find some negative charges to interact with, and the less positive will leave first.
Okay.
Okay. Well, all of this is recorded. You can listen to it slowly and try to grasp the information, and you can ask me again. I will go over it with you. All right, good. We'll stop here. This is what all the material you have for the quiz on Friday. So up to this lecture.